Hi, welcome to Math 119-312. I am trying a new way of doing the data presentation. I'm actually not going to project from my computer. Instead, the computer in the classroom is zooming into this class and is going to display my screen through Zoom, which is going to be there, and that's going to handle the multitude of HDMI issues. It's a little absurd to be doing this because sometimes it will mean that there's actually going to be a second or two delay between when I advance the slide and when it goes to the web, comes here and comes back there rather than doing it directly. But this way, starting on Wednesday, I will be able to write things down live and use the other device, which I spent all this money on. And I really want to use it after spending all this money on. All right, so what I want to do today is, as I'm going to try to do frequently, start off by discussing statistics and how we can manipulate people's perception by how we phrase things, or hidden stories that statistics tell us that we may not realize immediately. So I believe I've mentioned this one earlier. This is a plot of the sunrise and sunset times in North Adams, Massachusetts in 2020. It's showing us beautifully when it's today. Also looks like it's not displaying entirely all of the image. So you are missing some of the text at the end. I think you can figure out what the months are. I will have to deal with that later. Does anything look strange when you see this plot? Anything jump out at you? Yes? Yeah, the change to the daylight saving. So there's two places where all of a sudden we have this massive change, almost an hour in when sunrise, sunset is. And if you think about it, well, that's daylight savings, and that's why. And if you were to just take the orange curve and slide it down, or the blue curve and slide it down, you would see it would be a nice continuous change in time. So again, if you look at things carefully, there's often a story. Why do we have these 2 points? Something's going on. Something's a little bit different. All right. Anybody know which Super Bowl this is? 2 years ago. It could have been the other one. It could have been the first Patriots-Rams. But in the first Patriot-Rams, a lot of America was actually rooting for the Patriots. Times changed. There are at least two issues with this picture. Can anybody give me one issue? Let's see.
Hello?
Hello.
No.
When you look at this, is there anything that says, well, that's not quite right? Yes. Hawaii, Alaska. Actually, it's more than just that. It's also Puerto Rico. It's the territories. The United States of America is more than just the lower 48 or the 48 continental states. So we do not know who Alaska and Hawaii are rooting for. I would guess the Rams, but when you look at this, does any part of the country or any parts of the country look interesting or different? And can you tell me why they might be different from the rest?
Louisiana.
Excellent. So there's this little dot over here, which most people don't see. And the reason is the Rams used to be in St. Louis, and when they moved, they pissed off a lot of people in St. Louis who were willing to root for the Patriots. So that's one region. All right. Anything else that looks interesting?
Louisiana.
Louisiana. Why would people in Louisiana root for the Patriots?
Because
of the pass interference call.
Okay, good. So there was a pass interference call between the New Orleans Saints and the Rams. And after the game, the NFL admitted, yeah, boy, we really screwed up that play. There were multiple penalties that they missed. And the people in New Orleans and Louisiana were so furious that it was enough to have them answering these surveys rooting for the Patriots. Although really what happened is, from what I've heard, because I have friends there, they actually just, for the most part, didn't watch the Super Bowl. They actually played old Saints Super Bowls and watched that instead. There's one other part of the country which is an obvious explanation. New England. So it's not surprising that New England is rooting for the New England Patriots. But again, when you have a map like this, there's often stories behind small changes. Why is there a dot here? Why is this part of the country different? So whenever you see anything, I always want you to be focusing and trying to find those areas. Okay. So the next is I took a picture of my office door. In the old days, I could actually invite you to my office. We sadly can't do that. The first is an article from the Record a few years ago. They asked a bunch of math professors, what is your favorite constant and why? So we've already seen the Fibonacci numbers. Related to the Fibonacci numbers, one of the most important quantities is the golden mean, 1 plus root 5 divided by 2. And I said that that was my favorite number. It arises from the Fibonacci numbers. It possesses an incredible wealth of remarkable properties, including the fact that it equals the reciprocal of its own inverse. How many of you knew that the golden mean had this property? It is the reciprocal of its own inverse. Is this a remarkable property? Okay, why is it not a remarkable property?
Every non-zero number has it.
Every non-zero number is the reciprocal of its own inverse. Right? I basically said, I like the golden mean because it's not zero. Depending on how you phrase things, you can make very mundane things seem truly impressive. I have actually slipped this past some professional mathematicians. Really? And they start doing the calculations and they go, oh. So be very careful how things are phrased in terms of what words people use, how they try to phrase things. So the last is, if you look very carefully, you can see that there's some baseball stuff at the top of the page. And so I'll zoom in on this. So this is 2018, June 4th. And depending on which site you went to, the left was from ESPN and the right was from Google. Depending on which website you went to, they had a different ordering of the teams in the American League East as to who was in first place. ESPN got it correct and had the Red Sox in first place. Google had it wrong with the evil, dreaded empire of the New York Yankees in first. Why is there a difference? Yes. So it's interesting as to how you look at it. If you look at it by winning percentage, the Red Sox winning percentage was 683. The New York Yankees winning percentage was 685. The Yankees had a better winning percentage. So if you look at it like that, the Yankees should be in first because they had a better winning percentage. What's different between the Red Sox and the Yankees when you look at their numbers? I'm sorry? The game's behind. So it lists the Yankees as one game behind the Red Sox, even though they have a higher winning percentage. Why is that the case?
Because the Red Sox won more games.
The Red Sox played more games. So the Red Sox had 2 more losses and 4 more wins. So they were 4-2 in those extra 6 games. It is unusual for teams to have played 6 more games than another team. Something strange is going on. In those 6 games, the Sox winning percentage was 666. That's actually less than the winning percentage of the Yankees and the Red Sox for the other games. And so that was enough to lower the Red Sox down. But if you look at games behind, it's counted by losses and wins. And so in that metric, amazingly, the Sox came up first. The point of this is, depending on what case you want to make, you can often choose the statistic you want to view or display or emphasize or highlight to convince people one way or the other. If you are looking at serious research, what should be done is beforehand, you should agree as to what are the metrics going to be before you do the study. Once you have the data, you can often find metrics to support your case. All right. So now, turning to the main content, it's been a while since we've done the math calculation, so I thought I would just quickly review what we did last time and then start extending the mathematical models. And then for those of you who are taking it in 312, we will do a little bit more involved in that a little bit later. So the Fibonacci numbers are defined by the following. F0 is 0, F1 is 1, and then Fn plus 1 is Fn plus Fn minus 1. So each number is the sum of the previous 2. So it goes 0, 1, 1, 2, 3, 5, 8, and you see 8 is 5 plus 3. And we talked about why it's not a bad idea to guess that the Fibonacci numbers grow like R to the n for some R. And we saw how this could be used to model a bunch of things. We saw rabbits. If you watch the video, a generalization of this model is gambling in Vegas. There's a lot of things that can be modeled by this discrete equations. And we saw this by saying, well, we know Fn plus 1 is less than or equal to twice Fn, because the sequence is not decreasing. So that means it's growing slower than 2 to the n. Similarly, you can show it's growing at least as fast as root 2 to the n. So somewhere in between, and that's where you get the r to the n. So when we plug in r to the n and we substitute, we get r to the n plus 1 is r to the n plus r to the n minus 1, or r squared is r plus 1. And so we get the two roots, 1 plus or minus root 5 over 2, which does equal the reciprocal of its own inverse. And then you see that more generally, I could take any combination of these because this is a linear equation. And if you haven't done this before, it's a good exercise to just go through. In fact, I'll probably make this a formal homework assignment, to just go through and show that if R1 and R2 are these numbers, then anything of this form satisfies the recurrence. And the recurrence has the solution has two free parameters now, C1 and C2. And the reason it has two free parameters is if you look at it, this is a depth 2 recurrence. Fn plus 1 is defined in terms of the previous two values. So once I know any two values, the whole sequence is determined. That's why I need two pieces of information. And there's a lot of different ways you can talk about what those two pieces of information are going to be. I'm going to just call them the C1 and the C2. And if you go forward and just go through and do the algebra, if you want it to be the actual Fibonacci numbers, you get the following formula due to Binet, which is absolutely wonderful. It allows you to jump to any moment in time. You don't have to run the simulation. You can just jump anywhere. As we start looking at the more complicated models to describe virus propagation, it's not going to be so easy always to jump to the answer. We talked a little bit about trying to look at maybe modeling whales. And this was inspired by Star Trek 4. And we had some rules about how many new, is it calves that whales give birth to? The young whales called calves? Okay. How many calves does each pair give? And we could write down again a series of equations and we could solve it in matrix form. Didn't really talk in detail about how you would solve it, but just writing things down. Okay, oops, somehow this seems to have lowered it. Oh, all right. So what I want to do now is talk about what we ended at the last time, trying to model rabbits and foxes. So for simplicity, we will assume that there are no other animals in the world. We will assume there are no viruses, there are just rabbits and foxes. Can somebody briefly summarize what happens? Yes. Sorry, he raised his hand first. Foxes eat the rabbits. Anything else? Foxes eat the rabbits is only part of the story. Yes. Rabbits give birth to more rabbits. We're almost there. Yes. And foxes give birth to more foxes. Do we have to worry about foxes and rabbits merging and creating a new species? No. We're not going to worry about that. There's just foxes and rabbits. So let's let Rn be the number of rabbits at time n, Fn be the number of foxes at time n. We want to figure out how do these change as a function of time. Hopefully it's obvious, but just to make sure, why are we calling these Rn and Fn? Rabbit and foxes. You want to be able to quickly look down and see what is going on. Anybody know about the Battle of Trafalgar? All right, so what is the Battle of Trafalgar? Yes?
It was a naval battle between Napoleon and the British.
So it was a naval battle between Napoleon and the British. Who won?
British.
The British. It was a huge victory for the British. One of the greatest naval victories or defeats of all time, depending on which point of view you are. They celebrated the 200th anniversary of this battle, but so that no one would feel bad, it wasn't the British versus the French-Spanish fleet. It was, I think, red versus blue. You can do that. You can use names like that, but when you do that, you lose the advantage of being able to quickly look down and see what things are referring to. There is a difference between the British ships and the British crews, and when you have notation that reflects that, it can help you when you're looking at things. If you've taken calculus, we use capital F to denote the antiderivative or the integral of little f, so when you quickly look down, you see these functions are related. So when you're choosing things, I strongly emphasize you to write down good terms. If you've ever done any computer programming, you will see all the time people having really good names with lots of underscores of what's going on. Okay. So we want to start off with a very simple model. If we can't even solve a simple model, we have no chance of anything more complicated. So what do you think the values of foxes and rabbits at time n plus 1 should depend on? Simplest possible model.
Breeding rate, I guess.
Okay, I'm sorry, say that again?
Number of foxes and rabbits.
Number of foxes and rabbits at time n. So let's just keep it extremely simple. Do you think all that matters is how many foxes and rabbits you have at time n? Why not?
No.
Well, that could, okay, so the comment was, we need to know how many rabbits are getting eaten by foxes. We can incorporate that into our model. What I'm saying is, do we need to know how many rabbits there were at time n-1 or n-2? Or is it
Not really.
enough to know how many foxes and rabbits there are at time n? Think back to the real problem. What did we need to know for the real problem? Sorry? Just time in, but we did time in a very different way. What information am I claiming was necessary? Yes. So we segmented the real population into subpopulations. So in some sense, we can still do it as we only need to know what's going on at time n, but we need to know a lot more about what's going on at time n than just how many people there are. So when we're looking at rabbits and foxes, keeping things simple, if we just know the numbers of rabbits and foxes, is that enough? Or what else might you want to know? So the number of rabbits at each age. Do you have a segment of rabbit population that is no longer reproducing? If so, how many of your rabbits are in that group? I am talking to some people about some new models to try to explain how COVID goes. And one of the things we're talking about is maybe we have different types of human populations. And that as education happens, it translates people from one group or transfers people from one group to another. People, you now start to wear masks. And if you wear masks, are you a different population than people who don't wear masks? Do you socially distance? Do you avoid large gatherings? Do you avoid in-person classes? How much of this stuff becomes important in trying to figure out how the virus propagates? And so it's very simple to just say, here's how many rabbits, here's how many foxes, and we'll just have a rough rule that, look, on average, if we have this many rabbits, we can assume this fraction is reproducing. And that's not a bad first order approximation. But if you want a better model, you would want to keep track of how many you have at each level. But then need to know which rabbits are eaten by foxes. Which rabbits do you think are the ones that are eaten? Do you think it's distributed uniformly? Or do you think certain rabbits are more likely to become morsels?
Smaller, younger rabbits.
Okay, so I've got older ones, and I think I heard younger ones from the web. So from the web, why younger ones?
Because they're not skilled in surviving against foxes. They have no experience.
Ones might not be as skilled at surviving. These could be Ensign Redshirt from Star Trek, where they beam down to the planet and don't really know what to do and are very quickly killed. Why the older ones?
They don't have as much energy and ability to avoid all the foxes they find.
So the older ones may not have the same speed as the young, or stuff like that. Maybe the older ones don't go out anymore. But there's a lot of things you would need to know to try to make the model more realistic. Okay, so now we want to try to figure out how Rn+1 depends on Rn and Fn, and similarly how Fn+1 depends on Rn and Fn. So the simplest relation is to assume everything is linear. So we'll assume Rn+1 equals A times Rn plus B times Fn, where A and B are some fixed universal constants. And similarly, we will assume that Fn+1 is CRn plus DFn. Do you think this model is correct? No. Do you think it might be useful? Maybe. Yeah. It's at least a good start. It's a simple start that we can get our hands on. What's nice is if this is the model, if I tell you the initial populations of rabbits and foxes, is there any uncertainty in what happens? You can just plug this into Excel or any program you want, and you have an explicit formula for how many are around at the next level from the previous. It's completely deterministic. You know, again, you would probably not want to do this in real life. You would probably want to replace A, B, C, D with random variables that could fluctuate maybe around certain values. But as a first simple thing, we will be able to, or we should be able to, write down an explicit formula for Fn and Rn. Let's start thinking about the constants A, B, C, D. You should always be telling a story. You should always have some idea of what to expect before you get there. Once you have the stuff in front of you, it's very easy to be guided and led by the data. I will try to send you, or if somebody sends me an email reminder, to send one of my favorite science articles by Isaac Asimov. It's on the planet that wasn't. And the world was very different in the 1800s. To some extent, scientists were almost like rock stars at times, depending on what they did. And Newton's law of gravity was one of the greatest triumphs of science. And in the 1800s, Newton's law of gravity stopped working well with the orbits of the planets. One planet in particular, it was doing poorly. Anybody know which planet? It was the most recently discovered one. Anybody know what it was discovered in the 1700s? I'm sorry? Pluto was not discovered till much later. So the Greeks, and from that time on, we could see up to Saturn. And then in the 1700s, I believe it was Herschel discovered Uranus. And in perhaps one of the greatest ass-kissing moments in the history of science, decided to name it after the King of Britain, which pleased his liege, but did not please the rest of Europe. And so the rest of Europe said, no, let's see, you have Jupiter, you have Saturn. Saturn was Jupiter's father up to Uranus, which was Saturn's father. And so that will be the name. And the orbit of Uranus was not quite what theory predicted. So one of the possible explanations is the reason it's not quite right is Newton's laws are wrong. And Newton's law of gravity just doesn't work. Can anybody think of another explanation? Yes?
They didn't have the right data?
So what data might they be missing? So the comment from the class was they may not have the right data. What data might they be missing?
Other forces.
Other forces. So it could be that there is another force. And in one of my favorite science fiction universes created by Jerry Pournelle and Larry Niven, they actually went to an astrophysicist at Caltech, Dan Alderson, who created, I think, 6 pages of differential equations to model a fifth fundamental force to allow instantaneous transport from one part of a solar system to another solar system. But within solar systems, you have to go slower than the speed of light. So it could be that there is another force, absolutely. Is there a way to save Newton's laws and have Newton's laws correct and still have the orbit of Uranus not what we thought? What data might we be missing? So how would you calculate the orbit of a planet? What would you need? You would need the sun and the mass of the sun, and what else would you need? Mass of the planets. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus. These were the planets that were known. What might be missing? Another planet. What if there was another planet that was far from the sun? Well, the further away it is from all the other planets, the less impact it's going to have on them, and most of the impact will be confined to Uranus. And 2 different scientists predicted where the planet should be. One of them, Adams in Britain, was not able to convince the astronomers to turn their telescopes there. And I think it's Leverrier was the first one to get the telescopes pointed there and discover it. This was a phenomenal discovery. You know, before, when Herschel discovered Uranus, it was through observation and seeing something in the heavens. Now you actually have a scientist doing a calculation on a piece of paper, telling people, point your telescopes here and you will see a new planet. And it was there, and it explained what was going on. Phenomenal in terms of the power of science and the impact this had. Now, given that success, they looked at the rest of the planets and they noticed that the rest of the planets were a little bit off as well. And in fact, the one that was off the most was Mercury. So if you've just proven the existence of Neptune to fix Uranus, and now you know that there's an issue with Mercury, what would be a reasonable conjecture? Yes?
There might be another planet.
There might be another planet between Mercury and the Sun. And they named the planet Vulcan after the god of the forge. This was well before Star Trek. What might be difficult about discovering a planet between the Sun and Mercury? It's close to the Sun, so when you turn your telescopes, it's going to be very hard to see. There's only a few times when you might have a chance to see it. It's during eclipses. And so astronomers were told, when these eclipses come, here's where you should be looking. Most astronomers reported no planetary observation, but a few people did. And again, given the success in predicting Neptune, there was this belief that there must be another planet. And there was this push, I want to be the one to discover it. So when you're looking at data and you have a bias, it is sometimes extremely hard to control that. Is that dot? Is that something? Did I see something? And I really want you to be aware of this issue as you start going through the data, as you look at the data that is being sent to you by the world. Always ask who is giving you the data, what is their objective? Can you verify the data in another way? Why are they presenting it this way? And so over time, the telescopes got better and better and better, and they were able to decrease the size of the possible planet to the point where it was no longer going to be large enough to make any difference. And the solution doesn't come until Einstein and the general theory of relativity, that the gravitational field itself has energy, which is equivalent to some mass, which actually corrects all the planet's motion. So the warning here is to just be very careful about all the data that you're being given. All right, so here, again, stories. What story can you tell me about A, B, C, D? The simplest thing is, can you tell me anything about their signs? Which ones do you think are positive? Which ones do you think are negative? Yes? Which one is probably negative? Yeah, it makes sense that B would be negative. The more foxes we have, the fewer rabbits we should have at the next moment. All right, so I like B being negative. What else? Yes? So D would be negative, that the more foxes you have, the fewer foxes you have. Why would that be the case? So this thing gets really interesting. So they have the same food source, so are they competing with each other? So your answer is right and wrong. With the simple model, I think your answer is wrong. Because to really know what's going on as to are they competing with each other, we would really need to know how many rabbits are there. So under what condition do you think D would be negative?
If there's a fixed number of rabbits and it doesn't increase.
What kind of fixed number of rabbits?
Older, or I guess older rabbits.
Well, I mean, I may prefer
non-reproducing rabbits. So it doesn't increase the size.
Not quite on reproducing.
Less rabbits than foxes.
Yeah, maybe if there's very few rabbits, now the foxes are having trouble finding rabbits. If there's a tremendous number of rabbits, if there's a surplus of rabbits, then the foxes are not going to compete with each other. It's like, hey, look, have whatever you want. I don't really care. We are about to come to the Jewish holiday of Yom Kippur. Any baseball fans here? There's a very famous story. Sandy Koufax was the pitcher for the Dodgers who won the World Series. And game one was during Yom Kippur. And you're not supposed to do activities like this on Yom Kippur. You're supposed to go to temple. And he asked the manager of the Dodgers, is it okay? And the manager of the Dodgers said, absolutely. No worries at all. I understand. And one of the reasons he was willing to do this is he had Don Drysdale, another Hall of Famer like Sandy Koufax, on his staff. So So I don't use Sandy Koufax, I use Don Drysdale. It's not a big deal. I've got two wonderful pitchers. I'll pitch Koufax in game 2. An interesting twist of the story is sadly Drysdale had one of his worst outings ever, where Sheldon did not last long. And the story I've heard is that as he was being pulled, he said to the manager, "I bet you wish I was Jewish as well today too." If we have so many rabbits that the foxes can just say, "Look, you take these rabbits over here, I'll just go over here. It's not a big deal. There's no need to fight." Then the rabbits are not going to be a critical agent in the fox population, and I don't expect D to be positive. But as the number of rabbits decreases, and the fox are now competing, then that's going to matter. And what this is saying is maybe we need something more complicated than just a simple linear model. That somehow we have to take into account how many rabbits there are, where are they located, how quickly can you get to them. So we have thoughts about B and D. Yeah, I do think D should be positive as an initial thing. You know, maybe the rabbits, maybe the foxes are reproducing, or the foxes just aren't dying. You know, if the foxes just don't die, then they would just move on and D would be at least 1. What about A and C? Both positive. So if we have rabbits at time n, those rabbits give us more rabbits at time n plus 1. So it makes sense that A should be positive. And similarly, the more rabbits there are, the more foxes can prey on them and eat. And so you would expect that the number of foxes will be increasing with the number of rabbits. And so I'll put in red A, B, and C as I'm pretty confident about my understanding of the signs of them, and I will put D in blue as I'm less confident about the sign there, that I really think that one is a little bit different. So you can Google the web. I found a nice set of notes online. I've got the link right over here, and they gave the following model. For every 5 rabbits, 1 fox is born. Every fox eats 10 rabbits. Each rabbit produces 4 more rabbits. And I think they were doing things on a monthly basis. And so this gives us the equation Rn plus 1 equals 4Rn minus 10Fn, and Fn plus 1 equals 1/5 Rn plus 1 Fn. So these are going to be the values for a simple model, and we want to figure out how many rabbits and foxes there are at any moment in time. One of the things you have to be careful about is to make sure that your model doesn't return anything absurd. Are there any things that could be absurd? Yes? Yes, you could actually have the model that maybe one of the populations goes negative for a little bit and then recovers and becomes positive. Can you have negative rabbits? No, so as soon as you get negative rabbits or negative foxes, in fact, as soon as they get to 0, that's it, that value is gone, and then it just truncates. So be very careful only to use the model in situations where you believe it should be whole. So you could actually just run the Excel spreadsheet, look at where are you in 10,000 months, and if there was some intervening moment when one of the populations became negative, you can't trust any of the output from that point onward. Okay, any thoughts about how we might want to solve this? So we have 2 equations. If we had 2 equations and 2 unknowns, it wouldn't be so bad. If you had like x plus 3y equals 7 and 4x minus 6y equals 12, what you could do is solve for y in terms of x from one equation, substitute that into the other, now you have an equation just involving x. You find x, and then you plug that back into the first equation, then you get y. So if we have something like that, we can solve it. If you know linear algebra is a nice formal way to do the calculations. Over here, it's a little bit more complicated because we do have 2 variables, R and F, but they're evaluated at different times. One is at time n, one is at time n plus 1. So any thoughts as to how we could solve this? Or if you can't see at least how to solve it, how could we start to make something simpler to study? So what makes these equations hard is they're linked. Wouldn't it be wonderful if we had one equation that described rabbits and one equation that described foxes? That's similar to how you solved equations, two equations with two unknowns in algebra many years ago. Solve for y in terms of x, substitute. Could we use one equation to eliminate either rabbits or foxes in the other? How could we do that? Yes? Okay, so if I add them directly, I get Rn plus 1 plus Fn plus 1 equals 21 fifths Rn minus 9 Fn. So if I just add them directly, I'm still going to have everything mixed, but you're on the right track. So I could, okay, so which one do you want to solve for Fn? So if I do that, so you're close, so I get Fn is equal to Fn plus 1 minus 1/5 Rn. Fn is equal to, say, negative 1/10 of the Rn. When I combine them together, I'm still going to have the F's and the R's mixed up together because you're going to have that Fn plus 1. You're getting close. If we look at this equation is mostly an R equation. It just has one F. Whereas this one is mostly an F equation. It just has one R. I could solve for Rn in terms of the Fn's, or I could solve for Fn in terms of the Rn's. And so what I chose to do is I chose to use the second equation and write Rn is equal to 5Fn plus 1 minus 5Fn. I solved for the number of rabbits in terms of the number of foxes. And now I go back to the first equation, and every place where I see an R, I can replace it with a difference of 2x. And so when I plug that in now, I'll get Rn plus 1, so it'll be 5Fn plus 2 minus 5Fn plus 1, and that's the start over here. And then the next one is equal to 4 times Rn, so it's 4 times 5, that's going to be 20Fn plus 1 minus 20Fn minus 10Fn. And now I have an equation that only involves F. Now I just do some simplifications. So I get 5Fn plus 2 minus 25Fn plus 1 plus 30Fn equals 0. This is screaming at you to divide by 5 to make the numbers a little bit nicer. So we get Fn plus 2 minus 5Fn plus 1 plus 6Fn equals 0. So this should remind you of the Fibonacci equation we had. For the Fibonacci's, we had Fn plus 2 minus Fn plus 1 minus Fn equals 0. That's equivalent to Fn plus 1 equals Fn plus Fn minus 1, just shifting the indices around. The difference now is instead of having constants of 1 and 1, we have constants of 5 and 6. Well, we could use the method of divine inspiration. It worked for us before. Let's try it again. So let's guess Fn is u to the n for some u. I can't use R because R is rabbits, and I don't want to overload the system. So if I guess u to the n, I would get u to the n plus 2 minus 5 to the un plus 1 plus 6u to the n equals 0. So we get the equation u squared minus 5u plus 6 equals 0. This is a quadratic equation. How do we solve quadratic equations? One way is divine inspiration is to just look at it and say, I can see it factors as u minus 2 times u minus 3. How many of you were a little bit shocked that the numbers were 4, negative 10, 1, and 1/5? Did the 1/5 seem a little strange? When you look at a lot of lectures, people who actually care about their students often spend the time to cook up the numbers so that when you do the algebra, things simplify nicely. It is possible that this just happened to work out like this and the numbers were chosen randomly. I don't buy it. I think somebody started with, I want to make sure at the end of the day, I get a nice quadratic that factors with nice roots, like 2 and 3. and then maybe work backwards a little bit as to how you want the numbers to be. Sometimes, however, you can guess. My daughter is taking Algebra 1, and I was trying to talk to her about how do you solve, systems of, two equations with two unknowns. And I was trying to show her that not every point that's on one line is always on the other. And I just, randomly chose a point, and knowing my bad luck, what happened? It was on both. I happened to just randomly choose the solution. It can happen. If you see something like 2 and 3 in a problem like this, almost surely someone is cooking the books to make things nice. We have the
Hi. So
comment.
we haven't heard anything, right?
I'm sorry? Okay, so if you have the quadratic formula, if you forget to see just how just by inspection that it's u minus 2, u minus 3, you could use the quadratic formula to find the roots. As an aside, let me see if I can quickly. Shift to. Oh, maybe I don't have it. Okay, so because we have the quadratic formula, we can always play these explicit games and write down. Oh, here we go. I do have it. Go back and share. So I say, for the cubic, there is an explicit formula for the roots of a cubic. There is a reason you don't learn this in school. Negative b plus or minus square root of b squared minus 4ac over 2a, we can expect you to remember that. This one's a little bit more involved. And this is one of the 4 solutions to the quotient. Interestingly, there is no explicit solution for degree 5 and higher. So if I give you a more general recurrence, we will not be able to write down a closed form solution. But there will still be roots. And we can approximate the roots, and we can do a lot of the analysis, but we're not going to have the simple answers. It's nice when you have the simple answers, because you can then use this to see how changes in values will affect the dynamics. Coming back here, we have our quadratic, we factor it, we get the roots of 2 and 3. So if we were guessing fn is u to the n, 2 to the n and 3 to the n are the only solutions. And so the most general solution would be C1 2 to the n plus C2 3 to the n. And you choose the values of C1 and C2 to reflect the initial population. Once we know how many foxes there are as a function of time, we can then figure out how many rabbits there are by just substituting backwards. So what I want you to see from this is that the math we use to solve the Fibonacci numbers can actually be useful for a variety of other problems. And all that will happen if we make the system a little bit more complicated is it will change what goes on over here. Rather than using the quadratic formula, we would have to use something a little bit more powerful. And eventually the system might become so complicated, we can't write down an explicit answer, but we can numerically approximate the answer, and we can still do a lot of wonderful things. Right. Any question on this before we move on to now trying to model viruses? Okay. So concerns about, I'm sorry, let's do one last thing. Concerns about the model. So you had already mentioned some concerns about my choice of D being negative and the fact that the rabbits and the foxes, maybe the simple linear model is not quite enough. So there's a lot of different improved models. One of the most popular is the Lotka-Volterra equations. And you have gone to Wikipedia, source of all knowledge, fountain of all wisdom, and just pasted the beginning there. It's not a bad article. Instead of doing this as a difference equation where you have discrete time steps, we do it as a differential equation, so time moves continuously. You do not worry about solving the math like this if you're in the 119 level. I just want you to be aware of what's out there, where calculus starts coming into play. And now, some of this is pretty similar. How my rabbit population changes per time is related to how many rabbits I have. And now it's actually decreasing with the number of foxes. So now it's actually the foxes are preying on each other. And then the number of rabbits that I killed, it's now depending on this product of rabbits and foxes. And they're using this as a way to try to take into account how often are the rabbits and the foxes going to meet so that they can eat each other, or so that one can eat the other. And again, there's lots of different models you can do, and you can start asking, as I start putting in these terms, can I still solve it? If I can't solve it exactly, can I at least get some information? And so one of my Williams students from last year was kind enough to write up some notes. I will be sharing them later. We're just polishing up a few little things. Daniel Bernoulli, centuries ago, applied mathematics to model smallpox. Does anybody know anything about the history of smallpox or the current status of smallpox?
Eradicated.
Smallpox has been eradicated. Unfortunately, there are still stockpiles of smallpox in various places, but we have vaccines for smallpox. One of the dangers is, sometimes when you are doing these vaccines, people might die from the vaccine. And you might have to do very painful trade-offs. How many deaths is it worth to create a population that now has immunity that will not succumb to the disease in the future? And so he tried to come up with some differential equations to describe how people might move between various categories. We talked earlier, when we did the wheels, that you could be, just born 1 year, 2 years, 3 years old. In a lot of the virus propagation models, they have the S, the I, and the R, the SIR model. S stands for susceptible. It means you can be infected. I is infected, and R is recovered. And so you can ask, how do the number of people in each group change over time? So, I am just flashing the equations up here right now. We are not going to talk about them in great length today. What would you hope is true about the recovered population? Yes. That they're immune. It may not be the case that everybody who is recovered is immune. For a lot of disease, most people who recover are immune. If you want, you can almost always find an extreme counterexample. One of my good friends, we went to college and grad school together. His father had chickenpox twice. This is not supposed to happen. But most people will get chickenpox at most once. For most people, if you get chickenpox and survive, you move into the recovered category, and more than just that, the immune category. So the big questions in models like this is, how do you want to fragment the population? And so the simpler the model you have, the easier it's going to be to analyze. The more bells and whistles, the more features you put into play, the harder it's going to be to get a closed form expression. And you're going to have to resort to what? So we don't have a closed form expression. What are we going to have to do? Do we just give up our heads and say it's too complicated? So solve it numerically. Do our best guess. Have the computer maybe run thousands or millions of simulations. And then the problem is, what are some of the parameters? So my father was a double E in college. He goes off and starts working in high tech, and eventually he enrolls in a program to get an MBA. And he takes a class with a very academic professor who gives the class an equation with 46 variables to describe what your company should do in any conceivable situation. My father controls himself and just calmly asks, this is a very interesting equation. I don't know the values of some of these parameters for my own company, let alone the competition. And she just couldn't, but isn't it a beautiful equation? It tells you what to do. And my father just nodded and said, okay, thank you. You need to have the values for parameters. If you change the values just a little bit, how does it change the answer? How sensitive are things? One of the big questions about a lot of viruses is how infectious are they? How many people will each person infect? If each person infects on average less than one person, what do you think is going to happen to the disease? It should die out. If each person is infecting on average more than one person, what will happen? It should explode. And so this threshold is extremely important. Are you above 1 or are you below 1? If you're significantly above 1 or significantly below 1, then we have reasonable confidence as to what's going on. If you're very near 1, it's a very different story. So when you're looking at a lot of these models, as we're going to be later in the semester, I always want you to be thinking, which ones do I truly need to know? And again, one of my friends has testified before Congress on climate models, where he says for some of these models, if you change some of the parameters by just a small amount, you get a wildly different prediction. That doesn't mean that the models are wrong, and it doesn't mean that the parameters are wrong. It just means you have to be extremely careful about how sensitive the model is. And for those of you who are working with me on trying to come up with the right statistic for Massachusetts to color code, how strong is COVID? It has already been a great suggestion from one of our alums. We don't want a model that is so sensitive in small towns where one observation can make a tremendous difference. One false positive should not be enough to completely sway what happens. And we need to find better statistics. His comment was, what if we can start taking into account contact tracing? And we know that this person has been completely isolated, that they haven't seen anybody. So even if they've tested positive, if we know everyone they've seen and all of them test negative, it's not that bad of a positive, which is very different from somebody who tests positive and we have no idea where they've been or how many people they've seen. All right, so this is a good place to end. And so I'm going to send some emails about suggestions for what people want for the next class in terms of going into a little bit more detail for those at 312 or reviewing some of the math for people who haven't seen it for as long.